Hi everyone, my name is Minali Bouillon, and today I'll be presenting the results from my field experiment investigating periwinkle abundance at Point Pleasant Park and Oakland Park. Before I begin, I want to acknowledge that this experiment was conducted on Mi'kmaq, the ancestral and unceded territory of the Mi'kmaq people. I recognize that we are all treaty people and that we are all grateful for the opportunity to live, work, and experience this land. So my experimental question for this study was, does the level of wave exposure along cobble beaches affect periwinkle distribution? So the species that this study was specifically looking at was the common periwinkle, or Littorina littorea. This species is found primarily in temperate marine environments around the coasts of the North Atlantic Ocean. Previous research suggests that wave exposure and environmental stress play important roles in shaping the distribution of intertidal snails. A study by Davenport and Davenport from 2005 investigated how shore height, wave exposure, and geographic location influence the thermal tolerance of the rocky shore snail Nucella lapillus on a sheltered and exposed coast in Ireland. They found that snails living higher in the intertidal zone, where they had experienced longer periods of air exposure, were more thermally tolerant than those exposed to greater wave action. Although their study is not directly measuring the abundance of these snails, it demonstrated that physical stressors such as wave exposure and desiccation can influence where intertidal snails are able to survive and thrive. Similarly, a study by Eschweiler et al. From 2009 examined Littorina littorea population on sheltered sedimentary shores and exposed rocky shores. They found that sheltered habitats supported nearly 3 times more periwinkles than exposed sites. Although the individuals were generally smaller, the authors suggested that strong wave action reduces juvenile survival by dislodging snails before they can establish, while sheltered environments allow higher recruitment despite increased predation and parasite pressure on larger individuals. Together, both of these studies indicate that physical conditions and biological interactions influence periwinkle populations. Building on this research, my study investigates whether differences in wave exposure along cobble beaches affect the abundance and distribution of periwinkles in Nova Scotia, with the expectation that sheltered sites will support more higher snail densities than more exposed locations. So the locations that we were working at. So our study was conducted on June 3rd of 2026 across Point Pleasant Park and Oakland Park in Halifax, Nova Scotia. These sites were selected based off of the ability to access the beach and the presence of a cobble intertidal beach ecosystem, which allowed for direct comparison between these two different locations. So the data collection at Point Pleasant Park was carried out during low tide. We arrived at around 4:25 p.m., which gave us a bit of like a 30-minute buffer time between the scheduled low time, which was at 4:54 that day. So this allowed us time to set up and make sure that we had all of our things measured before we started the surveying. We recorded some environmental conditions, so this was water temperature, air temperature, and wind speed. To record the water temperature, we used a digital meat thermometer. Air temperature and wind speed was recorded using our iPhone's weather app. We as well also noted our GPS coordinates at the time of the start of the experiment. So while we were surveying the Point Pleasant area, we realized that we needed another location to continue our results. So we relocated to Oakland Park to represent the sheltered intertidal zone. We arrived at Oakland Park at around 6:10 p.m., which was slightly after the low tide time of that day, but we predicted that the amount of time that had passed was not enough to significantly affect our experiment. At Oakland Park, we carried out the same surveying of the area as well as recorded the same environmental data. So our experimental design. We laid 2 15-feet transects. The first transect was laid at the low tide line, which was 0 feet, and the second transect was laid at 4 feet above from the low tide line, and this represented our mid-intertidal area. There were 4 quadrants laid per transect, totaling out to be 8 quadrants. Each quadrant was 50 centimeters by 50 centimeters, and these quadrants were placed using a randomized selector. We used a random number generator to determine the spacing of the quadrants along our transect. As well, a coin was flipped to determine whether the quadrant would be placed on the shore side of the transect or the water side of the transect. For each quadrant, I also recorded an estimation of snail abundance while in the field. These are pictures of some of our quadrants from Point Pleasant Park. You can see here that we used PVC pipe and duct tape to make our quadrants, and then these are some of the quadrants that were placed in at the Oakland Park site. So some of the results. Image J was used to count the numbers of periwinkles per quadrant. This was then entered into Excel to find the means and calculate standard deviation. For Point Pleasant Park, the mean in the low intertidal zone was 3, and in the mid-intertidal zone, the mean was 6.5. On the other hand, for Oakland Park, the low intertidal mean was 21.75, and the mid-intertidal mean was 31.25. Off of observation alone, you can see that these numbers are drastically different from each other, and here you can see it on this bar graph, Oakland Park plotted against Point Pleasant Park, with the low intertidal zone in the dark and the mid-intertidal zone in the lighter gray. And you can see, again, off of observation, that there is a clear difference in the means at both of these sites. This is another bar graph that was plotted that looks at, it shows you the entirety of all the data points that were taken, as well as that dark black line that represents the mean. So in our studio, a two-way ANOVA test was taken to determine whether the periwinkle abundance significantly differed between the Oakland Park and the Point Pleasant Park for low and mid intertidal zones. So does exposure to waves affect periwinkle abundance? We found that there was a significant effect of site exposure on periwinkle abundance, with an F value of 15.896 and a P value of 0.0018. At Oakland Park, there was a significantly higher abundance than at Point Pleasant Park, and there was no significant effect found between the low and mid intertidal zones, as well as no significant interaction between site and zone. So from these results, we can determine that wave exposure on cobble intertidal zones significantly changed the abundance and establishment of periwinkles, but not between the low and mid intertidal zones. Overall, our results showed that wave exposure had a significant effect on periwinkle abundance, with many more snails found at the sheltered Oakland Park site than at the more exposed Point Pleasant site. This supports our initial hypothesis and agrees with the findings of Esch-Wheeler et al. From 2009, who also found that sheltered shores tend to have higher periwinkle densities. Strong wave action can dislodge snails, especially juveniles, making it more difficult for populations to establish themselves in exposed environments. More interestingly, we did not find a significant difference between the low and mid-intertidal zones. This may be because we only sampled 2 elevations, so the environmental differences between them were not large enough to affect abundance. Other factors such as substrate characteristics, food availability, or predation may have also influenced these results. There are several limitations to this study that I want to point out. First of all, we only sampled 2 sites with a relatively small number of quadrants, and wave exposure was solely based on observation rather than any direct measurement. This means that some of the differences we observed could have been caused by other environmental factors. While we did find significant results for the relationship between periwinkle abundance and the exposed sites on the cobble beaches, these limitations do change how we can interpret it and conclude the actual results. Because this experiment was conducted on such a small scale and only 2 locations were being used, due to this, the results could very likely be a result of chance. Further testing would be required in order to be certain about the correlation between periwinkle abundance and wave exposure, alongside the fact that there was little to no environmental data taken in order to determine the level of wave exposure, with the exception of our own observation while on site and the geographic location of where we were sampling. Further information regarding the frequency and extremity of wave action in both sites should be taken over a longer period of time to determine if there is really a significant difference in wave exposure at the exposed site and at the sheltered site. I want to point out that traditional scientific methods mainly focus on quantitative data and often fail to incorporate a deeper perspective of our experimental findings. So highlighting the practices of Indigenous peoples and incorporating a more dynamic understanding of our environment can give us further insight into ecosystem dynamics and allow for a broader understanding of the quantitative trends found in these types of studies. Thinking about how long-term effects of our work while in the field, as well as consciously and mindfully understanding the inner workings of these ecosystems that we are working in is very important. And implying this in our practice, I think, can actually give us more information about how we can interpret our data rather than just taking it at face value with the quantitative understanding. Uh, this is just some of our acknowledgements and some references. Thank you.